Okay, hello everybody, and welcome to this week's video, in which we are continuing the endeavour of working through the Magnetohydrodynamics questions from Jackson's classical Electrodynamics. And this is question 5 out of 7 from the first edition. Let's immediately begin. So, 10.5 says, the force equation for an electronic plasma, including a phenomenological collision term, but neglecting the hydrostatic pressure of zero temperature approximation, is dv dt plus v dot del times v equals E over m bracket E plus v over c cross b minus v times vector v, or rather nu times vector v, where nu is the collision frequency. Part A, which we'll do first, asks us to show that in the presence of a static, uniform, external electric and magnetic fields, the linearized steady-state expansion for Ohm's law becomes J sub I is the sum of all j's of sigma ij E sub j, where the conductivity tensor sigma ij is omega p squared over 4 pi nu bracket 1 plus... Did I misread that? I think that's supposed to be omega nu squared. Over 4 pi nu 1 plus omega b squared over nu squared, and then a matrix, 3x3 matrix reading 1 omega b over v 0 minus omega b over nu 1 0 0 0 1 plus omega b squared over nu squared. And omega nu omega b is the electronic plasma precision frequency. The direction of b is chosen as the z-axis. Wonderful. Let's begin. So we'll start with the phenomenological force equation for an electronic plasma. Electrons with charge minus E, which is equivalent to E, and mass m, and will negate hydrostatic pressure, as said in the question. Neglect, not negate. Sorry, neglect. Just basically the same equation. That's not a partial. dv dt plus v dot del v equals E over m E plus v c cross b minus... How am I going to make my news look like news? I could do that. As long as it's kind of clear. There must be a better way of doing this. That's alright. I'll do that. That's a new. I think that's clear. Now for a steady-state linearized approximation, we can just assume that partial derivatives are 0. Or not assume, that's kind of the definition of steady state. And we'll neglect this second order term. So basically this whole side becomes 0. So it becomes a balance of the Lorentz force and then the collision drag. So we get that E over ME plus E over MC. I am expanding here. V cross B naught. I forgot that. Minus. That'll do. Because it doesn't look like a gamma. A gamma would be like that. Whereas this is just like that. And my V is like that. Yeah, those are separate enough. And B naught here is the static uniform external magnetic field. E naught will be the static uniform electric field that we're dealing with eventually. No, it won't. It'll be EXYZ. Apologies. Now we'll define our current density J. as n0 eV, where n0 is equilibrium electron density. So we can sub that into this equation. V hat is J over n0 E. And so from, I forgot to say this equals 0. From that we can sub in that new J, also rearranging slightly, is n0 E squared per m times the electric field plus E over mc J cross B naught. Now we're told that the z-axis is aligned with B, but we need to do this for B naught, so we can align it such that B naught is B z hat, and so we can take this cross product J cross B naught to be B, that's not a Y, JY x hat minus JX Y hat. Neither of which will be in our Z direction. We can then introduce our plasma frequency from before. It was P, I kept reading out new, my eyes aren't working. It's because I can't zoom in on here with my pen. My mouse is charging, it's too far away. So every time I said omega P, that does make more sense. Sorry, I did read these. I wrote these notes last week, and it has been a very long week. Okay, so omega squared P is 4 pi n naught E squared over m. Oh, and we'll also do omega B is EB over MC. We'll keep signing in here consistent with the final matrix. Yeah. So new J is omega P squared per 4 pi E plus omega B J Y x hat plus J x y hat. Cool. Now we have linear equations, a linear system of equations even. We can take individual bits of all of these in x, y, and z. So if we take it in x first for our, I'll do it by electric field. So if we take electric field x first, we'll have omega p squared per 4 pi E x is new jx minus omega b jy. Not very good subscript, is it? And then for y, omega p squared per 4 pi ey is omega b jx plus new jy. Yep. And then finally ez is just going to have a direct jz term. Cool. So we have our system of equations. This is the nicest one because we can just send that new to the other side. Therefore, j sub z is equal to omega p squared over 4 pi nu. That's not looking like much of a nu anymore. I don't like it. It is worrying me. I want it to be very clear that this is still a nu. Alright, that's okay. And then jx and jy can be solved for. which I'm going to do now. So, sticking things together, I think we will multiply this by nu, and the second one will multiply by omega b, and we'll add them together. So nu squared plus omega b squared jx is omega p squared over 4 pi nu ex. And we can get jx on its own here. EY, yeah, cool. And we can do the same thing, but this time eliminate jy, jx even. And actually, by symmetry, the only difference is that this coefficient will be negative and by the x, so I'm actually just going to write that in because it's not very confusing as to where that comes from, I don't think. If you just look at these equations off of inspection, you can see where, by subtracting them, you get that from. So jy then is omega p squared over 4 pi nu 1 plus omega p squared per nu squared. That's like a gamma, that's like an either. So as I said, that coefficient is negative, and on our ex component. Right. And it wants us to write this, LBook wants us to write this as a tensor matrixy form. And so it becomes fairly clear that we can, well, first of all, we can write it in the form J equals sigma, where sigma is our tensor, dot E. Obviously, we've got our components there. Now, taking that, we can also take our JZ. That's just going to be equals omega p squared over 4 pi nu 1 plus omega p squared over nu squared times 1 plus omega p squared over nu squared. And then that will give us it in the form of this coefficient. So we can write sigma ij in our final form, omega p squared over 4 pi. I never learn, every time that's in the wrong place. Right. 4 pi nu 1 plus omega p squared per nu squared. Boom. Over omega p squared. And now times, in fact, I'll do the brackets afterwards. 1, and then our coefficient here is omega b over nu, 0. This is minus omega, I'm not going to have a space, minus omega b over nu, 1, 0, 0, 0, 1 plus omega p squared over nu squared. Yay! And so we have derived, or not derived, but we have shown that under these conditions, these very simple conditions, this electronic plasma can give us Ohm's law. This Ohm's law, which is definitely not the nice Ohm's law, the kind Ohm's law. Anyway, actually I always forget to write part A. Anyway, what does part B say? Suppose that at t equals 0, an external electric field E is suddenly applied in the x direction, there being a magnetic induction B in the z direction. The current is 0 at t equals 0. Find expressions for the components of the current at all times, including transient behavior. This sounds like a differential equation. Yeah. Yeah. Who would have guessed? When you're working with partial differential equations, you have to solve a differential equation. Who would have known? So, right. So we can write our field E as E times x hat, and B is still BZ hat, and J of 0 is 0. Now we have our time-dependent linearized equation from before, so dt is omega p squared per 4 pi e plus omega b j cross z hat minus mu j with an n. Now we can separate j into components. So j dot x is omega p squared per 4 pi e minus nu jx plus omega b jy. Now j dot y is minus nu jy minus omega b jx. Finally, jz is minus nu jz. So since we have that Ez is 0, let's write down some more things. Jz of 0 is 0, and Jz of t is also 0 for any t. Wait, I can say given all. Can you do that? Is that the right circumstance to use that? I don't know. I'm trying to get better at using the formal mathematical notation and stuff. I don't think that's correct. Given all jz of t is 0, given, or shouldn't it be, because this is a function, given all, for each t in t will be the natural numbers, jz t is maps to 0. That's a mathematically correct statement, maybe. I don't know, I'm not a pure mathematician. Right, moving on swiftly and getting rid of that abomination. To solve the coupled XY system which we have remaining, we can take a complex current here. So we'll take J plus to be Jx plus I Jy, and we can then add the first equation to I times the second equation. So J plus is omega p squared per 4 pi e minus nu j's x rather plus I j y minus I omega b jx plus I jy. Nice. J dot plus, in fact doing this right again, that's then equal to omega p squared over 4 pi e minus nu plus I b j plus. Nice. For obvious reasons, I think. And that gives us a first order differential equation in J plus. And we have a general exponential decay solution that I'm going to pull out of my notes because I'm not going to go through and solve this with all the coefficients. It would be a pain. Anyway, J plus is, this is just it's literally dj dt is equal to something plus something j. It's like a y equals mx plus c of differential equations. That will leave us with, in fact, I should probably note that this is the function, is omega p squared e over 4 pi, I'm putting that all over, nu plus I omega b plus k e to the minus nu plus I omega b t. Obviously we get the nu plus I from our formulation of J plus. Now we can extract or rather we can split it up into real and imaginary parts. This is going to be quite big. Omega p squared e per 4 pi nu squared plus omega b squared times nu minus I omega b. Now, I'm going to put a square bracket there. 1 minus e to the minus nu t cos omega bt. That is all part of the cos. Plus I e to the minus nu t sine omega bt. That's actually quite good. I thought it was going to take up more space. I also think it's correct. Yeah, I was just expanding that, it's not that hard. I've got to say what k is. K is just that. I could write that again, but I'm not going to. For obvious reasons, when j of t is 0, then t is 0. K is minus that, sorry. When j of t is 0, that's all 0. E to 0 is 1. So k plus that is 0. So k is minus that. And then this just comes from Euler identity expansion. Basic things, I would hope, at this stage. If you're doing magnetohydrodynamics, probably not needing to worry about things like solving the constant from the differential equation or Euler expansions. Anyway, let's split it up and take the real and the imaginary parts separately. So we can get that j sub x of t is omega PE squared. I will never learn, will I? 4 pi nu squared plus omega b squared, omega p squared e times nu 1 minus e to the minus nu t cos bt plus omega b e to the minus nu t sine bt. Yep. And then jy of 2 is omega, nope, I'm not going to do it this time, 4 pi nu squared plus omega b squared. Oh look, I didn't even need as much. Isn't that wonderful? I guess I am learning to write it smaller. Omega p squared e. And this will be nu, this is just going to be swapped over, e to the minus nu t sine omega b t minus omega b, or minus e to the minus nu t cos omega b t. And that is our complex first order differential equation solved to give us our two functions that express the current density. We did in fact find expressions for the components of current at all times. Transient behavior is the last thing. So we can brain these functions. I'm probably not going to write it down here, but note that as t goes to infinity, the exponentials are decaying exponentials, so they go away. And so this is what we're left with, and this is sigma with indices x and x for the x1, and sigma with indices x and y for the y1. Yep. Oh, sorry, y and x, not x and y. So yeah, that shows that it returns back to its state. It returns back to the steady state after, as time goes on. Or rather, it tends towards the steady state as time goes on. But we'll never reach it again, even theoretically. Anyway, probably put a box around that, and then that's everything. So I hope you very much enjoyed this video. Have a nice week, and I'll be back next week with question number 6. Oh, put a box around it. That's what I was going to do. Anyway, see you next week. Bye-bye.